So I'm going to talk a bit about Ohm next. I'm not going to spend too much time talking about like Lisp, or I'm not going to spend too much time explaining like all the language-specific aspects. I think for this audience, it's more fun to see like what are the basic concepts, and these concepts I think are transferable. If you're doing any type of UI work, it really doesn't matter what type of UI work you're doing. I think it's relevant. So just a little bit. Oh yeah. So starting off with the Steve Jobs quote. I love this quote. Yeah, he's a very quotable person, but this is one of my favorite quotes that he said. Design is not just what it looks like and feels like. Design is how it works. So I've been a UI programmer for about a decade, and I take this very seriously. So I've done all kinds of UI programming in all different kinds of contexts, and I really believe this. Like, in order to have a good user experience, it actually really matters the way that the software was engineered. If you get it wrong, you're going to end up with a very bad experience. Okay, so a little bit about myself. I've been doing, again, UI work, mostly JavaScript stuff, though I've played around with Java, done some Objective-C, familiar with iOS, and so on and so forth. A bit of OpenGL at one point, so on and so forth. But I was at the New York Times for 4 years doing JavaScript there. I was very lucky I got to work on this really crazy thing. This was the live coverage of the 2012 election. So I wrote this whole dashboard in CoffeeScript. And this was, I think there were like 4 million page views in, I don't know, 2 hours. We transferred like 19 terabytes of JSON. It's pretty crazy. But so there was a whole live component. This was pre-React, and so this was all custom CoffeeScript code where I wrote code to constantly fetch from a cached Rails endpoint, and we had to constantly diff the content because what was happening is that people were, of course, making mistakes in the posts, and they wanted those things to change immediately, right? And so what they would want to happen is this title might be wrong, right? They want to invalidate the cache, and they would want to have the front end polling the endpoint, and I would have to calculate the diff so they would show the correct post without screwing up the rest of the timeline. While that was happening, we had this was live. All this stuff was live. The headlines were changing. We had live results coming in. So this was a interactive map written in JavaScript. You could zoom down to the county level. We were loading in results as they were happening. All this stuff, the whole thing. And so it was a big crazy mess. I mean, it was a success. People were very happy with it. But I was like, that was really hard, and that was a lot of work. And I would say after that, I started thinking, there must be a better way to do this type of stuff. Again, as exciting and as cool as that project was, some of the takeaways for me, and the reason that I have a certain perspective on this stuff now I know next, is that we had a system and there was far too much state. It would often be the case, for example, somebody would make some sort of mistake and there would be a bug. And of course, the thing is live, and so you're like fixing the bugs and then hoping that the deploy happens quick enough so that users don't see bad stuff. Especially on election night. Like, this is the worst time to make a mistake because it might actually change the news. It's very frightening. So far too much state. So I've been thinking about how can we, if we're doing UI stuff, how can we have better abstractions for state? Something else that I didn't like about the way that I'd done things for the past 10 years was synchronization is really ad hoc. You have components randomly going to get stuff. This increases latency. Worse experience, and it's hard to reason about if you have all these different components all doing things on their own with respect to synchronization. And then the worst part about it all was that you're in production, and then you have very simple errors, simple bugs, very simple UI problems that somehow didn't get caught by the type of testing that we had, nor by large amounts of human QA. So eliminating state. So the first thing that I'm interested in is getting rid of this. Again, this story is actually improved, right? And completely out of the blue, React appeared, which is Facebook's thing. And this was actually designed by this gentleman, Jordan Walk. And he had been writing a backbone app at Facebook. And he'd sort of reached his the end of his line, right? And again, this is not like, I'm not talking about, you can be effective with Backbone. People are doing cool stuff with Backbone. It's not anti-Backbone. It's talking about one developer's distaste with how much work and effort it took to reason about the system. So he designed something called React, and he told his boss, look, I'm just going to make this new thing. I'm going to actually just re-render everything always from scratch. And they were like, that's the stupidest idea we've ever heard, but you seem like a smart guy, so go ahead and try it. And then 6 months later, he showed his first demo of React, and it was faster than the apps they'd written using Backbone. So that was a very surprising thing, though if you know anything about web technology in the DOM, it actually goes back to computer graphics. There's a huge cost to flushing, right? So the problem is that when you touch the DOM, the browser often wants to repaint, right? So if you were doing OpenGL, this is like when you flush the buffer, now you're going to need the graphics card to sync, and that's an expensive thing to do. You actually want to batch a bunch of operations and send a nice big chunk of work. And that's the principle behind React. So what's interesting is that React delivers, we're just going to re-render the entire state of the thing, but it turns out because we do intelligent batching, it's not as expensive as you would think. And the beautiful thing is that you now have something that's very easy to reason about. What's easier to reason about, a big mess of state or a stateless web page that just renders HTML? Right? One of these things is easier than the other, right? React is sort of going back to this very nice, clean web model, which was stateless web page. There's no state in the page. It's just a view. So the other thing that I use for Next, but it's not necessary, is Clojurescript. And the thing I like about Clojurescript is Clojurescript has a very large set of high-performance persistent data structures. So it actually has immutable data structures. So you have this cool thing. We can take React, which is this very clean stateless rendering model, and we can take this stateless data structure model and we put them together. And we'll get a lot of benefits out of this. Things that seem hard, like, something went wrong, let's just rewind. Like something like an error happened, we just want to rewind the application or recover some previous state. Something that would require you to manually piece together an uncorrupted state. Immutable data structures give you a simpler way to reason about that. So that's the big benefit of Clojurescript. We're taking stateless rendering plus immutable data structures, and that solves some of the state problem. There's, of course, more subtleties. Okay, now the other thing that I said was a problem that I didn't like is sort of the client-server thing, which is clients, the way that people write UI code, because most UI stuff these days is not on one person's machine, it's not a desktop app, it's actually some distributed application. Right? It actually adds a huge amount of complexity to an application. It used to be, the user works on local data and there's no latency. Latency is not something you have to think about, right? And now suddenly people are like, the user's going to favorite the thing and we don't want to wait 1.5 seconds for the server to say that it got favorited, right? But now you have this problem where it used to be you could just favorite the thing. You now have to write stateful logic to say favorite it now and rewind it if it fails. So what used to be a simple change is now a complex sort of state negotiation. And so I think a lot of complexity happens here. And so can we rethink this problem? Can we start thinking about how can we manage state given the fact that there's network latency? So some awesome ideas happening here. I can't dig into too much of these things, but highly recommended reading after this talk. So Facebook has a new thing called Relay. Relay sort of is a thing that they pair with React. They're starting to build apps with it. And Relay does this really awesome thing in which that instead of having components randomly request resources from the internet, what they do is they have components, and each component has a query. The query says, I need this little piece of thing. And then that component has subchildren, as like children, right? It's like a tree of components. This is what UIs are like. And some subchild says, well, you're going to get that thing, but I'm going to need this thing. And add my little bit to your bit. And then all the way down. So you have actually a huge query. And instead of actually, when you boot up your app, 20 requests happening from all your different subcomponents, you send one thing. Because you can do a bunch of benchmarks. And far more expensive than a large response is separate responses. There's actually hard limits on how many parallel requests you can even make in the browser. So this is a very simple optimization that takes into account network latency. It's a very cool idea, and actually Next just steals it. The fact that components actually have fragments of the query. That means we can always compute the total query and make one request. It's pretty slick, and we'll see that. Completely independent of Relay. So Relay was announced February this year, totally separately because Relay was a secret. Netflix invented something very similar right at the exact same time, and they announced it a month before. So they announced their thing in January, and then Facebook announced their thing in February, and neither people knew that they were working on the same problem. So Netflix had built a very traditional sort of REST-based network stack for their wide diversity of clients. So they have to target set-top boxes, mobile phones, iPads, desktop computers, so on and so forth. That's a lot of clients. And what they wanted to do is like, well, we want to be able to share these endpoints, right? Wouldn't it be nice if each client could say, well, I'm mobile, I only need the title of the movie, a small thumbnail, and the short description. That's the only thing that can fit on this screen, right? Whereas the desktop client's like, no, just give me everything, right? So, and there's huge benefits here is that the mobile client can now request exactly what it wants. It gets a very small payload, and then makes a difference on how responsive the application is. Again, this is true for whether it's set-top boxes or whatever. But so they did the same thing. So similar to how Relay allows an application to describe exactly what it wants from the server, Falcor also does this. The syntax is different, the sort of feature set's different, but that's not what's important. This talk is about what are the big ideas that people are coming up with that actually, what's the commonality? And we'll see, how Ohm sort of distills some of these things. So Ohm Next. So Ohm Next takes, again, React, it takes Clojurescript because we get the stateless views, stateless models, and then it takes a bunch of these ideas about how can we deal with this network latency problem and the synchronization problem. So the big ideas about how Ohm apps work, these may sound radical and you may not do things this way, but I'm surprised. So Ohm is about 22 months old now, almost 2 years, and some of these ideas are finally taking traction in the JavaScript world, which is really cool. So the way that Ohm works, all application state is stored in a single atom. What's nice about this model is that you can always, if you've ever done it, it's really cool for debugging because you always know where to look. All your information is in one place, and you think, that sounds crazy. Don't you want to put all your state in different components? And you're like, well, imagine if you did databases that way. Your life would be horrible, right? That's not like a fundamental piece of your architecture is a database, and the beautiful thing about a database is all your data is in one place, and you have a way to examine it. So we're going to just adopt the database model. We're going to put all our state in one place. Another thing that we're going to borrow, if you're fans of Ember, so one of the awesome things about Ember, which I think is actually a rock solid idea, is that Ember uses routing as a core abstraction, right? To talk about how do we do reads. Does it actually can you do mutations through routing as well in Ember? Okay, so they don't do that. But still, it's a central way to talk about the state of the app. If you change the URL, that'll change the presentation. And that actually is still important. You can change the URL and the application state changes. But we're going to get a little more aggressive with that good idea that Ember had, that Ember really took from the design of web applications. So all state reads and writes go through one abstraction. But again, this should sound familiar. So before, where did Ember get that idea? Well, I got it from Rails. Where did Rails get that idea? They got it from REST, right? REST is this very clean notion of, how do we transfer state to clients, and how do clients transfer state back to some remote thing? But we're going to actually take that and say, that's a great design. We're just going to put that design on clients. It's not just for remote. We're going to actually use the same design, even if it's all local. And the last thing, we're going to add declarative queries, and they're co-located with components, and we'll see why that's cool. That might be harder to understand without seeing an example. So we have these 3 points, these 3 big ideas in Ohm. They're all copyable. It is not specific to Ohm Next. If you want to copy them, you can. But one thing that I think is important if you pick this design is you have to have some sort of sensible messaging model. If you look at Falcor, they have a syntax. They have a way to communicate reads and writes. It's very clean. Similarly with Relay. Relay has a whole thing called GraphQL. And GraphQL actually gets serialized into a JSON AST that can be interpreted by a GraphQL server, so that there is a very strong a property that we'll talk about here in a second if you actually describe what's the relationship between the message and the response. So client-server models, they're good. They work. Now, people often look at this diagram. This is like some network model. But it doesn't matter if it's a network, right? If you can look at an OpenGL architecture diagram, and it looks exactly the same, right? It's solving this problem in which you have some powerful thing, whether it's a remote service or it's your graphics card. It wants to be communicated to in this very specific way, and in order to optimize this, you have the same problem, right? You can't just be chatty with this thing. This thing that has all this as a superpower, in the same way that your web server is kind of this super powerful thing. You can coordinate all these users. It's amazing. A graphics card can basically give you amazing graphical capabilities, but you have to talk to it in a specific way. It's well defined, and again, batching is a huge idea to make that work better. So what does a message look like? So we'll look at what a message looks like in OM next in a second. So what does a message look like in a typical web application today? JSON. This is like, it's basically, JSON took over. I actually remember, like JSON really was like not even really a thing to about 2008. I mean, people were kind of doing it, but you were like afraid, like Douglas Crockford starts as like, just call eval. That's okay. And then not okay. So when JSON really became a thing and every browser started supporting it and they started having high performance parsers, then really JSON became a thing. It's like, oh, okay, we have good, fast implementation of C in every language. Actually, it has these nice properties as a data exchange format in that humans can understand it. Like you can look at a JSON payload and you can understand it. It's great when you're building clients. You can just hit the endpoint, see the JSON. In fact, in Chrome, you can like pretty print that thing. And this is pretty slick. It makes people productive. This part of JSON is great. But here's where it gets problematic. You send some JSON to some endpoint, and what does the response look like? Well, it looks like JSON, but what correspondence does the response have to the thing that you asked for? What relationship does it actually have?
It's the thing the server decided was appropriate.
So was exactly what the server decided was appropriate. So was there anything in the thing that you sent that will let you know what comes back? Exactly. Hopefully. It's often not the case that the thing that comes back has very deep correspondence with what you sent. And so this, I think, is actually a terrible thing. And it's unacceptable for the way that the internet works. Like the internet could not work if this was the case. It's unacceptable for OpenGL cards if this was the case. And so the radical idea here is that no other serious messaging system works that way. You don't make requests for things and then get random responses back. There's usually a very close correspondence to the request and the response. So we're just going to make this, we're going to just do that. So yeah, so just to reiterate, what do clients get in the systems that people build today? Whatever the server wants to give you. It's almost always in the wrong shape because the client, whatever the client specification was changed yesterday, and they didn't put you on the email thread, right? You just don't know because they just changed what it had to be. Now the server response is wrong for the UI that you're building. This happens all the time. So you have to like munge the data on the client, and then it changes again, and then whatever you wrote to munge the data is wrong. Again, it's almost always in the wrong format. Somebody decides, oh, I want to use this ISO format for dates, and then you write the code for that, and then somebody decides to change that. And your code, again, it's wrong. And then you see NAN, right? And it's always too much or too little, right? So what happens is somebody decided this is the amount of information that a client needs. And then somebody says, well, now you got to write this mobile client, and it needs to load in like 2 seconds. And then the payload is 500K. And you're like, there's no way. It's impossible over 3G to load this thing in 2 seconds if you're sending me a 500K JSON response. Like the last time I looked, Twitter sends back 1 megabyte JSON responses. You can't load this in 2 seconds. So this is a huge problem, right? People on the back end just dictate too much about what a client's going to want to get. Okay, so let's fix this. And again, you don't have to. This is how OM next works, and it's just one possible approach to this problem. So we have query expressions in OMNext to deal with this issue. The approach is actually borrowed from something called Datomic. I work on Datomic. Datomic is very cool, and we're just copying one little thing. OMNext doesn't actually have anything to do with Datomic at all. It's just that we copy this little syntactical thing, and I like it because it's very simple. It's actually a lot like JSON. What does a query expression look like? So it's just a variant of something called Datomic pull syntax, and I've modified it a bit. It's not really a strict superset, but it's a better suited for generic messaging. Datomic pull is a bit too restricted in what it lets you describe. It allows us to do the things that you want to do on the web. When you hit an endpoint, you want to be able to parameterize it, right? URL plus URL parameters. You need to be able to parameterize something. You can represent mutations. So in REST, you could do this by saying it's a put or it's a post, right? You need to be able to talk about what does a mutation look like. So we can do this as well. And of course, we need to be able to parameterize those as well. So this is what it looks like. It's like this. So there's some remote endpoint, and in this world, there's only one endpoint. It's just the endpoint can basically route on the expression. And what this says is, here's a vector. This is like a JavaScript array. It's a Clojure vector. And I'm saying, I just want to read the address of something, the street address, right? Just give me back the street address. That's all I need. Now, imagine somebody writes a different client and they want more, or they can handle more information. And what would this return? This would return a dictionary or a hash map, whatever you want to call it, JavaScript object. The return value would be a JavaScript object or whatever with just this entry and its value. So you're always going to go from, this is basically describing, these are the keys that I need. These are the keys that I care about. It's just a list of keys. And we're always going to go from a vector to a map-like thing. So I write a different client. I say, well, actually, I want the street and the city and the zip and the state and the country. Again, the syntax doesn't really matter. It's just that these are the keys that I want. Give me these keys. Right? Order doesn't matter here. We're just going to get back dictionaries. Orders doesn't matter. And also, raise your hand if you have questions, too. It's OK. This is meant to be not just me, like, ranting for an hour. So any questions so far? Any at all? OK. OK, so a query expression, to reiterate, is a vector of keys. The response will always be a map containing only those requested keys. I just fixed the problem, right? I did so little. I just said that if this is what I asked for, I'm going to get that back, right? There is no discrepancy. It now requires no transformation on my side, right? I know I can never make a mistake, right? I can now have great confidence in that whatever I requested is exactly what I'm going to get back, and I can now write a UI around that. And in fact, it's resilient to changes, right? As long as some jerk on the back end doesn't go change the keys, I'm safe, right? So there's a huge class of errors that just went away just by me being able to say, this is what I want, give it to me in this shape. And just to be clear, and we'll see this, this structure is fully recursive. So it's very much like GraphQL and Falcor in this way. This could be arbitrarily nested, and it will return back a nested structure in the exact shape that I wanted. So for example, if I wanted to do, well, I'm trying to think actually. So you could imagine, yes. Sorry for the highlighting. Oops. All right. Oops. So this up here should be like this. So what this is saying is, I know this person has an address, and this is a recursive thing. This vector is kind of like the outside one. This is saying this is a join. I know that in the DB that the person's address is actually a join. Find that thing and then only pick these keys. And this would actually return a hash map that has this one thing, and then it has a hash map which has the values for these keys. So it's fully recursive, which is a good fit for the type of thing that people already do on the web. People generally return nested JSON responses, and you go and you pick out the things that you need, except here now you can dictate that structure. So it used to be people handed you some arbitrary JSON structure. You just have to read the docs. Here I can get precisely the structure that I actually want. And Valcore and Relate already work this way today. They already work this way. So there's no novelty that I'm not introducing anything new here over what they've already done. OK. As I said, query expression is recursive. Each key itself can be a query expression. And then the question sort of becomes, well, what can appear between those things? You've seen a little bit about that, but we're going to break it down just so you see more examples. So simple reads, so I could be, you'll always want to wrap, but for example, you could imagine these things are nested, themselves in vectors. So the most basic thing is I want some key, right? Address street, or I want this key first name. And then we also support this thing called lookup refs, where you can actually have a vector. It's a 2-element vector. And this is a way to say, I know there's something in the DB and it has a unique key. In this case, this is silly. It's not unique, but it could be, right? This could be a unique thing. Person by email, and there's the email address. This is a way for me to look up some identity in the database based on some convenient syntax. For example, if I don't want to transmit database IDs across the wire, this is a way to deal with that problem. You have some other notion of identity in your system that you want to use.
By name, is that convention? You say by whatever.
Everything I'm showing you is by convention, right? So there are no the syntax is this grammar of the syntax is very specific, but as to what the keys themselves are, it's all by convention because we don't. I mean, again, this is why people like JSON. It's flexible, so this system is flexible in the same way. You can basically define what your keys mean.
So do you also say that keys could be their own query? So would you do something like submit a hash map where a key is person by name Bob and the value might be a vector of the keys you want to pull out of that person record? Is that kind of how you might use that?
That's exactly right. This is a key. I could actually put this in a hash map and say, I only want these properties from Bob. Okay. That's exactly right. So the whole system is designed to be self-similar, there are no edge cases. Like wherever a key is actually allowed, put it there, and the syntax still works. So that's just go ahead.
So is this just a spec, or is this a server-side component, or?
So we'll see. You might think, oh, this must be really complicated, but actually to make this work, it's 100 lines of code on the client and the backend. So there's a thing called a parser, which is already designed to understand this, and you just need it on the back end and the front end. And it's so simple. The grammar is so simple. You could write it in 100 lines of Ruby. You can't express very much in this system. Yet it's again designed to be as general as whatever you were already doing with JSON. That's a goal. So you want to parameterize a key. So there's a tuple syntax, but with curly braces instead of vectors. And this says I want to parameterize something. And you've got your keys, and all the keys that we saw before work here. But I can say I want some hash map of named key value pairs, which is parameterizing the query. So just like imagine this is a URL. Squint. It's a URL. You've attached some URL parameters to the URL. That's all that's happened. I just have a different syntax for it. What's the benefit of the syntax? There's only one thing we're getting here that URLs didn't give us. Yes, that's literally the only thing. The only thing that we're doing changing is recursion. You can arbitrarily nest these URL-like things. So if I wanted to get some window of results, if I wanted to give me this thing, but I only want MIME type plain text, whatever. Okay, so you need to be able to represent joins. So this is where it gets really annoying in REST because REST doesn't have a discipline about joins. The way that a traditional REST thing, you're just supposed to go back, right? You get a thing and it has links, and then you just go back for more stuff. So we want to get rid of that because we want to batch. So here we have joins. So we've already seen this to a degree, but here, I'm saying I know there's going to be multiple to-do items, and for each one, I want to pull out these keys, right? Or here, I want the friends, and I want for each one of the friends, I want these keys. Or for this person by email, which is a more realistic example, I want the address street for that person. So this works. This could work over collections, right? You could have many-to-many relationships, or one-to-many, or many-to-many, or whatever, and you can join in data. Does that make sense? But here you're not locked into anything about the endpoint, right? We can arbitrarily nest these things. And so now clients don't have, now when I'm writing a client, I don't have to be, please, 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 please add this other resource into the response. The client has the freedom to just get that thing that they need.
One other quick question. When you submit something like that last map there, does the response contain the vector, or does the response contain like the representation of the person?
So good question. So the question was, what will this look like? So in this case, you would get a key in a hash map. It would be to-do items. It would be a vector of results from the database in which each element of that vector only has these keys. So down here, this is obviously a unique thing. So this will return a hash map with this lookup ref, and then the value for that thing, which is only another hash map with address street in it.
So the response would have that vector as the key.
That's right. This is the key. So, that's why I kind of highlighted them in blue. These will never change. Like whatever you asked for, this is what will appear in the response.
So the friends returns friends is the key, and then the value is a vector
Of hash maps, which contain only those keys.
So is the response always going to be a vector of 0 or more items? Or
Not necessarily, because you could imagine that, again, like down here, this is a join, but it's like, it would not come back necessarily as a vector. It would just be that one thing. So that's something where it's like, that just depends on what your database, or however you wrote the endpoint, whether this is, or many to, one-to-many or whatever. But we don't specify that because that just would make this overly complicated, the syntax. But that's right. It's like one little fuzzy thing where it's like it's not well defined. You can parameterize your joins, and this is just to show all the things in combination. So I can be, give me the to-do items, and I want to start at 0 and end at 10. I want all my friends, but I want to filter the muted ones. And again, none of these things are hard-coded. So the whole point is for it to be as generic as, it's just you can make up whatever URLs you want. You can make up whatever parameters you want. OK, so the first thing you should be thinking about is, well, that's really cool, but what happened to my HTTP caching, right? What happened to I used to be able to just throw varnish in front of the thing. You could have tens of thousands of people come to my URL, and then everything would be OK. But how do you, if clients get to say whatever they want, how do you cache that, right? There's nothing stable to cache, right? If clients suddenly are in full control. And actually, Relay and Falcor both shipped without a good answer to this problem, right? So everybody, whenever you hear the talks, they're like, well, no, we've solved caching. And they have. There is actually a good caching story in that the caching happens on the client, so they minimize refetching, but they don't solve this problem of, I have a site, most of my users don't need dynamic requests, there's going to be a ton of people rushing to the site, I want to be able to serve something from HTTP cache, right? I just need to be able to do this. And you can't really do it with Falcor or Relay. So I decided I'm going to fix this because there's a specific nature to our syntax, and there's a specific way that omnext works that allows us to recover HTTP caching. So when I worked in the Times, we had a URL like this. This is dashboard items. This was the static URL. Every single person, all 4 million people, loaded this one. Actually, let's say actually a better example is not the election dashboard, because that had no interactive component. It would have been the Oscars dashboard, right, which had like 1 million viewers. And we wanted to serve the same dashboard to all of them. But that dashboard allowed people to favorite things. It allowed them to like answer quizzes and do surveys, all this stuff, which is really annoying because we would get like 1 million views, and 40,000 people that actually did all that stuff, they create 90% of the load, right? This tiny fraction of of our users are creating all the load because they have to be served dynamically. There's no way to cache what they're doing. But at least we could partition, right, these two categories of users. The people that are just want to consume the feed, and the people that actually need to actually run dynamic queries to do their interactions. So a great example is, well, there was our static URL, and then our dynamic URL looked like this. So we would make two requests. Everybody got served the first thing. Then we would check, is the user logged in? If they were logged in, we would run their dynamic query, right? And of course, we would switch to relay and Falcor style caching, which would be like, once you got this, unless they do something, we're done. We're not going to pull for this at all. So this is driven by the user. So this caching model is very similar to relay and Falcor. So people often look at relay and Falcor and think, this is a lot of novelty, but actually, everything they're solving is stuff that people are actually doing right now when they build apps. They're already doing this stuff. You just don't have a discipline around it yet. Okay, so we can fix this problem, right? So we've seen what queries look like in OhmNext. And so you can imagine you have a query that says, I want all the dashboard items, and this is something we haven't seen yet. It's called a union, in that we know that in the dashboard items there are going to be multiple types of content. There's going to be posts and photos and charts. And we may want to sub-select based on what's in the feed. For each type of thing, we want to sub-select certain keys for a particular type of thing in the feed. Right? This is a heterogeneous list. That's what dashboards are. You present different types of content. Now, here we say we want to grab the user's favorites. Now, what to do? I mean, how could you cache this? Because isn't this one big message? Isn't this just one big message? You couldn't cache this, because this is the part that's messing everything up. So because it's a data structure, right? It's a data structure, and because it's a data structure, it's not a string. It doesn't require parsing. It's actually data, in the same way that JSON is data. We can identify. It's actually very easy for us to basically compute. Select the part of the query that's the static part, and select the part of the query it's red because it's dangerous, which is the dynamic part, right? And in fact, if this user wasn't logged in, it would just be this. But the moment the user is logged in, we actually want both, but we do want to go for the static thing, and then request this. This is the thing that everybody goes for, but we want to have a combined thing for users that are logged in. So because this static part is known, we can just use traditional hashing techniques. Right? This represents some basic string. It's a string. It's not changing. Every user has the same thing. Right? Every user needs this. You can just convert this into a string and just SHA-256. That's all you need to do. And then you can make a separate request for this part. And it's because the data structure is trivial to split these things apart. It's literally filter out the static part and only send for the dynamic part. Right? So hit this URL for the part that's static, and hit the raw API for the part that's dynamic. Does that make sense? So simple. And again, it's because we picked a very simple thing, and it's easy because it's data to separate out the parts. Think about this. If it was a URL, you would have to grep the whole thing and pull it apart. Because the data structure, we literally can go filter. Right? It's basically literally filter. Okay, so let's see the demo. So here I have, I can't, if people want to see more stuff, they can, but I'm gonna keep this pretty simple. So here I have just an old to-dos MVC thing, which I was just trying to get basically working. And let's just demonstrate. Sorry. Let's just demonstrate something basic here. And hopefully this is still working. Demos are always scary. OK. So I wrote this against Datomic. You could have written against anything else. It doesn't really matter. I just used Datomic because I was like, this would be fun. It's the same to-do MVC you've seen. It's a little bit outdated. I haven't updated the CSS. But it's the same type of thing you've seen people do a million times. Except that it's not using local storage. I'm talking to a database, and you saw that it worked. This is all OhmNext, right? And in fact, if I click down here, you got all this cool stuff happening. We can click on network. What? Here, where are we? Console. Do I have to make this bigger? Here we go. Okay. So here, you see what I'm talking about. Because the thing was data, I'm using transit to encode the message. We're basically taking a Clojurescript data structure and encoding it into JSON. And this is actually, it's hard to see now, but this is actually the query expression. This is the same stuff. It's just now encoded into JSON to be sent over the wire. That's the response. Let's actually look at the request. The request is a mutation call, and it's just a list, and it's saying update this thing, and we want to, where is it? Set the completed to false, because I unchecked it, right? But it doesn't matter what I do; it's just one endpoint. So if I go here and I go, if I decide to change this, I say, get, OJ, and I press enter. All these different types of requests are going to one place, right? They're all going to one place, and I'm actually building up these queries. And so let's just see what this looks like. If I go here, if I scroll down, and you can ignore all the stuff that doesn't have anything to do with the query. So it's the same thing I showed earlier. The to-dos component, which would have been like a React component, has a co-located query. So it says, I'm going to want the to-dos list, and I don't know what I need. The next component class will tell me, right? So there's a huge benefit to the recursive thing. It's not just about clients getting only what they want. I can now split my queries apart and spread them across the components so that I can be, you work on the to-do item, I'm going to work on the big list, and you can change your keys, and it doesn't affect me at all, right? It does not affect me at all, right? It allows people to be focused on their components, and yet we're all coordinated by the same system, right? Instead of everybody deciding, this is how I talk to the back end, I can muck with my keys, they can muck with their keys, everybody mucks with their keys, but it's always going to be an efficient thing. You're always going to get one request. So if I go look at to-do item here, and I scroll down, you can see, we want the ID of the thing so we can update it. We want to know if it's in the edit state. We want to know whether it's complete, and we want to know whether it's the title, right? And of course, if I remove this, it would just break the UI because you wouldn't be getting the keys that you need. But actually, let's see this. Let's see this. Where's the API call here? Here we go. Let's look at this one. And let's look at the response. Where is it? Here we go. Response. The to-do list. And if I scroll over, I see to-do completed, get OJ, false, walk dog, so on and so forth, right? And that was literally just what we did. We just asked the root, give us the total query. It sends the total query, and I get back the exact thing. And you could look around this code. There's no code for reshaping. Nobody has to reshape anything. Nobody has to change the data, right? There's a direct correspondence between the query that is in each component, the request that we're going to make, and what we get back can immediately be given to the UI to render, right? You never have to transform the results. There's no transformation of the results. So this error-prone process of fixing the data, this just eliminates an entire class of problems just by allowing components to do things this way. So let me, go ahead.
If you make a request like if you completed to do, does it send the whole query again, or is it
No.
just a piece? Just sends the
So it's not like we get rid of the good ideas about REST. REST is a great way, people often write an endpoint and it has a specific ID. So what we actually do is we actually have the backend understand mutations aren't nested. Mutations are like you send a mutation, it's just a top level thing saying to do, update to do, and it's just a list, and the server is just going to interpret it right then. And it will just send back saying, we change this thing and we'll update just that thing. So there's a lot of tweaks to make it work so that you don't send full queries, because that would be expensive. Yeah, but good question. So let me show something that's traditionally very annoying to do. That's a lot simpler in this system. So we're borrowing something out of a page from Falcor. So Falcor has a very cool thing, which is that it allows you to write a router both on the front end and the back end. And if you can do this, and the client doesn't know how does the routing happen. So the client talks to this router on the client, and then that thing forwards to the server's router, and then gets responses, and then this thing merges it back. And the reason this is cool is because it gives you optimistic updates without complicating your front-end logic, right? I can say, router, I want to update something. The local router can actually give me back the updated thing, forward it to the server to actually run the thing, return the response, and this router can trigger an update if it turns out that it didn't work. But the nesting of the routing, right, the fact that I write code and I don't really care where it runs, allows me to write very simple logic for optimistic updates. So I'm going to show you, this is the update in the back end for updating a to-do if I change the text, right? So here's the updating code for, so here. So this is actually talking to Datomic. I mean, again, you don't have to understand everything about it, but we're just saying we're actually talking to a database. We're transacting against the database. We're saying, is it completed? Then set it to completed. If the title changed, yada, yada, update the thing in the DB. And then this is all the code for updating a to-do. And then if we look at the client-side code, we also have that action on the client. This is the whole notion of that we have two routes. One is the route that the server is going to run for this key, and then this one's the client's going to run. And this is literally all the code I need for optimistic update. I don't need any more code than this. In fact, I'm going to just disable optimistic updates right now. So if I remove the client-side optimistic update, and I just refresh, and what are we going to see? Right? Now, if I want it to come back, that's it, right? That's big, right? I mean,
So you would sort of soft commit that locally, and then if sending the update failed, then you would revert it?
so what will happen is that the server will send back the truth, and it would revert it. And you could go into a whole so React actually has pretty cool stuff. There's a lot of problems we don't solve. The React component can do things like, okay, I see that this update is not the one that I had before. And you can basically put control logic for error handling into components, because React components already know about state transitions. So that would probably be the way to do error handling. It's like we did an optimistic commit, and you want to tell the user, didn't work. So there are hooks in React itself already for doing this. We may add deeper hooks because I suspect as people build systems, they'll be like, we just want more control over error handling than what I currently implemented. But we'll just have to see what people want. But as far as it is right now, there's enough inside of React itself to do basic error reporting if you want to communicate something went wrong. But the fact that this is so trivial, it's big, right? This is the type of thing that you always get wrong. It's not quite right. You waste a lot of time on it. And also the fact that what does this mean for a front-end developer? And you want to understand what an update means. You're like, well, I know it's called this, and it has to be called the same thing on the back end. It has to be the same thing because we picked a message format, right? Once you pick a message format, your ability to reason about what your system means goes way up, right? Okay, so I'll show one other thing. So this is also fun, and I'm just going to show one little thing about this. So another thing that I really like is that, so if I go here and I click, so down here you'll see because we're using immutable data, you can rewind to whatever point you want. We actually record all last 100 states of the application, all 100 of them, and you can change it. If you want to record 10,000 transitions, you can. And persistent data structures, they're efficient. It says a bunch of things. It says this to do with this ID transacted this transaction, and it gives you a UUID for the state that it was before the transaction was applied. I can use this to rewind my application, fix a bug, and then I can just copy and paste this and reapply that transaction.
UUID for the app state, then, not just that?
That's right. This is the UUID for the local app state. So often when you're debugging, normally you just have to tear everything down and recreate it. So here, the framework is, if you're familiar with like fix and continue, which is this thing that people have always wanted, the fundamental model here is fix and continue. So you're developing, and then you have a bug, and you're like, well, I don't want to have to go back here. You can just rewind, fix your code, and because it's Lisp and we support hot code reloading without blowing away the state of your app, like you can actually change your code, keep the state alone, right? Fix the bug, and then actually, click the UI and okay, it worked, and you can keep going. So we're fixing. So this is what I'm talking about. The things I talked about at the beginning, we're not trying to fix one thing. We're trying to fix a lot of things all at the same time. Does that make sense? Okay. So enough about that. Let's see something else. Okay, so I'm almost done. So something I just wrapped up really recently is testing. So if you see that we have this really crazy model where we have it's basically an atomic transaction model for the UI, right? Everything is there, and we can always go backwards. That means you really truly have snapshots of your application state. Once you sort of adopt this model, things that would be quite a bit harder to do, because going backwards in time gets really hard unless you have some sort of very sophisticated command pattern in place. Whereas we've made that trivial. We said, no, screw that. We're not going to do that. We're going to use persistent data structures. You can always rewind. Once you do things this way, then automated testing, like you have really crazy possibilities there. So I draw a lot of inspiration from Qvik. Qvik is a company in which this person called John Hughes works. And let's dig into what Qvik is all about. So Qvik actually uses their technology for something else, and we'll get into that. But here's the problem. So I've been doing UIs for again, 10 years, and testing them is really, 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 really hard. It's very frustrating. And it's actually harder than almost anything else, because it's not quite like a backend. I mean, there's a nice thing about backends is that you got your database, you got your endpoint, leave me alone. Not my problem, right? There's a lot of testability because the model is very simple somewhat simpler on the back end with regards to the state space. But UIs have this problem. What people often do is they write mutable components, and the mutable components interact. The view abstractions are often mutable themselves, like the DOM, and people like, I'm going to stick some state in the DOM, and that state's there, and it's not in the model. So this means that the set of possibilities of states in your application gets really big, and this is a problem. And then what happens is that this happens. Everybody knows this happens, and then people come up with tools to address this thing. But of course, the tools can't fix this problem. You already lost here. Game over. And so what happens is that people try to sort of patch over with these tools. You have things like Selenium. But people are trying to do things with Selenium that are impossible, which is that once your model's mutable, once you recorded state in the DOM, Selenium's not going to buy you anything. It's not going to buy you anything because your mutation model is too hard to reason about. No tool is going to fix this. So what we'd like to do, if we can shrink this, we can fix this problem. Right? If we can do something about this problem, we can, I think, have a better idea about that problem. Okay. So one possible solution, I don't know if this is really going to work, but I feel more positive about it than other things that I've seen, is property-based testing. Came from Haskell. Lots of good things from Haskell. If you haven't checked out Haskell, I definitely recommend checking it out. But this idea first appeared in Haskell. Haskell is a very cool language. Everybody should check it out. One of the people that designed Haskell, John Hughes, he took this idea that they did in Haskell the first time, and then he's really taken the idea much further. And he's actually a great public speaker. He's spoken all over the world about property-based testing. I'm like, go watch any of his talks on YouTube. They're amazing. So he took property-based testing. He wrote a much more sophisticated implementation in Erlang with a bunch of interesting people at Cubic. And they actually had a really great success story where they certified 500 embedded computers in one of the new Volvo models. Right? So what they actually do is they take this 10,000 page specification of what every little computer is supposed to do. And they do something that they weren't able to do, which is actually, not prove, this is not a proof, but actually show that all the computers were broken. Right? And not only could they say, not only do they tell the designers of these components, because the way that cars get made is that you basically outsource to the cheapest vendor for that part that you need. So there's no coordination between these parts. Different vendors provide all these different computers. So how do you know they're actually going to work together? That's a huge problem. With Quick Check, you can do this amazing thing where somebody will say, no, there's not, they'll say, no, there's not a bug. We know there's not a bug. We do all this testing. And John Hughes and his team would be like, actually, if you do this operation and this operation and this operation, it breaks. Try it. It's broken. Right? So Quick Check does a crazy thing, which is if you use traditional testing methods, you will not find these problems. Right? They just don't work. So Quick Check does this amazing thing where it actually says, given a model, produce some random sequence of events. It's truly random. And actually, they use pseudo-random number generators because you need reproducibility. What happens is that you run this thing for 15 hours, and you see something fails, and it took 100 steps. But because they use this thing called generators that they took from Haskell, they can take 100 steps and shrink it down to the minimal case. And in fact, we're going to see this applied to UI testing. Even though you may see 5 actions, the model says we can shrink this back to the 2 or 3 actions that caused the failure. And that's huge because it's no good to get bug reports that give you 20 steps. Right? We know this. We'd rather somebody tell us, just show me the 2 steps that makes it fail. That's better. So watch the talks. Totally awesome. OK. And just to be clear, just to reiterate, this is not just generative testing. So a lot of people say, just make random data. This is not about generating random data. If you generate random data, you cannot shrink. So that's the huge thing about property-based testing, is it involves shrinking to find minimal cases. Shrinking. It's super important. It's also really important that the way that it's currently done is they use it's this monadic thing. It's very functional. Probably the best reason, this is probably the only legitimate reason I've ever found to actually learn anything about monads. Because this is awesome. Because if you understand how monads work, it allows you to build models that can thread state. Because, for example, in a UI, a user makes something. Well, that's a resource. You have to construct an ID, right? Some ID got generated when somebody click create. Well, the next event better use an ID that was created previously, right? And by using what's called bind, you can thread state into your generator so that you actually have a series of user interactions that make some sense, right? That actually makes sense. The state of each step, the next action, is predicated on previous actions. This is extremely important. Things like ID creation. OK, so let's see a demo. So here I have a very simple application. There's nothing to see. We're just going to actually just try this out. So I made a model. And my model is very simple, but it's typical. It's a friending app. I have people. They have some IDs and they have some names. They have some empty friend lists. There's some boring OM things that I just don't have time to talk about. We're just going to skip. Here we see things like, this is like parsing again. If we read people, then figure out what those people are. This is where it gets important. Mutate. So in the same way that we can do reads, we can also do mutations. So here we have something that will take the state of the application and basically friend somebody. And by friending somebody, all we're going to do is add up here. We're going to add somebody to the friend list. In fact, what we would actually add is something like this. Person by ID 1, right? It's just saying this person is friends with this person. Of course, and we're going to see this is a corrupted state if I don't do this, right? So in our simple model, it should not be possible for A to be friends with B if B is not friends with A. Because what that means is that you would have something that the user would see that's inconsistent. I clicked friend, and they appear in my list, but they don't appear in some other part of the UI where it needs to be present. Okay. So there's a bug. Even if you don't know Clojure, there's a bug here. I don't have the corresponding friending operation. I only add them as my friend, but I don't add me to their friend list. There is another bug in which that there is no precondition preventing self-friending. This ID and this ID could be the same, right? And then we have corresponding actions for remove friend and mutate friend. So let's see if this, let's make sure this is still working. Is this working? Yes, it's working. Okay. So I'm going to go, I'm going to quick check. I'm going to say generate 100 random sequences of events. Oh, actually, before we do this, let's see this. So we need to be able to generate random user interactions, right? So we need to be able to create these events that a user might trigger. So let's just see what this looks like. So I'm going to go gen sample, gen tx, add, remove. I want maybe 5 of these. So we saw, this is just query syntax, right? This is the query syntax we already saw, right? It's just, this is a mutation. Mutations look a little bit different in that the keys are not symbols. They're not keywords, they're symbols, but otherwise it should be familiar. We remove a friend, we add a friend. Then we have something where there's nothing in the transaction. Here we add a friend, we remove a friend, we remove a friend, we add a friend. Right, so this is awesome. This is literally as if somebody was clicking on the buttons, right? On the buttons. Except we don't need a person to click the buttons. Okay, so let's check this. So quick check, 100, and we want to know if no self-friending. And let's just see what no self-friending does. This should be sort of obvious in that like it takes something and it says, is the ID present in itself? Just like the friends. Am I inside that friend list? And the property-based test, all it does is takes the random generated actions and it runs these operations on the data. So here we say, given this parser, because we need to parse the transactions, we need to actually apply them. So here I can normalize the data, put it in some state, and do this. This is all the mocking that I need, by the way, which is also really awesome. Right? I don't need to see anything. Right? I don't need to look at anything. It's just like, is the code fundamentally right or wrong? Before we even get to rendering, we want to know that something is impossible. So let's see what happens. And this is where it gets really cool. Does that work? Now let's check this out. So this is cool. So this is where I was talking about. So I said test check 100, and look how big the failing case was. Look how long it took to find the failing case. Add. This is the only thing you actually need to look at. So this was all the random actions it took before it found the failure, and then it reduced it back to the smallest case. Now it's obvious what went wrong here. Right? You could just literally look at this and be like, what? ID 1, friend 1? Doesn't make any sense. So let's fix that. Okay, so if we go up to add friend, we're just going to add some code. We're going to go if not equal ID friend. And what we're going to want to do, return the state. This is fig wheel, so live updated. I don't need to do anything. Boom. So it generated 100 random user interactions, and it says after 100, we couldn't find any cases. Let's say, wow, come on. Well, what about 1,000? This will take 10 times as long. Oh, what happened there? Oh, so that's just, I apologize. That's actually just a bug with the IDE. But if we had run this like a node or whatever, that wouldn't have timed. So the problem was actually IntelliJ timed out before getting the result. But whatever. You get the point. Okay, So let's see another bug. So we have another thing, which is we want to test friend consistency. Okay, and we're going to make that smaller. So friend consistency is the problem of if I add a friend, we need to appear in both lists. I need to appear in their list, they need to appear in my list. Let's check this one. And again, you have a huge series of things, right? A bunch of things, and it says the simplest case is if you add even one friend, it doesn't work, right? So after all the random things, it still finds the most basic case. It's as if there's a friend. It's really if you had a friend to be like, look, here's the bug. Like it's actually explained to you almost in plain English what the bug is, right? So let's fix this case. So up here, we fix this bug. And then we want to go, well, we know we want to update person by ID and friend. We want to update their friends. And we want to add us, ourselves. OK. Well, let's see if that worked. What happened? Still a bunch of random things, a bunch of random operations that said, well, if you add a friend and then you remove a friend, you have the bug. Like, what? OK, but this is a good hint. This is a good hint. Let's look at remove friend. Oops, what's wrong here? There's no corresponding remove. There's only one of the removes. So let's go update in person by ID. Whoops, friend. And what I love about this demo is that it'll always tell you when you're wrong. So I'm not so worried about live coding, right? OK, so I think that this is the right. This is the right code for this. And let's do that. Boom. That's it. So what's really cool about this, if you've done, go ahead.
So you have these constraints that you're testing for?
Yes.
Why are the constraints not part of the model? Like, why are you passing them to quick check itself rather than baking that in and then just having quick check verify after every action? Does that make sense?
Verify after every
So,
action.
Like, you have like a friend consistency thing. You could just check like after every update to the model if that's true. And like bake that into the app itself and into the model. Because like basically here, like the model isn't, when you're updating the model, it's not doing any constraint validation itself. Right? You're doing constraint validation as part of the quick check thing.
But where else would I do it?
Where you're updating the model. Like,
You mean inside the application itself?
yeah.
I mean, I did that by fixing the bugs.
Right.
So remember, the model is not my program. Like the model is somewhere. Like when I say model, I don't mean model like MVC. I mean I modeled my program. What is my model? Is you have friends, people. You have these two operations, and then I have these constraints that I want given that universe of things. Now, does my program correspond to the quick check, that's the model, right? And then what I do is now I fixed my program to correspond to the model that I desired, right?
You're talking about like if you just bake those asserts like into like the update action.
You of course could do this, right? But that's assuming you knew to do that. That's like this allows me to say somebody found a bug. It took 10 steps. That's all we know. That's the bug report. It took 10 steps. Well, how do you figure that out? So what I'm saying is that now you have a system in which you can say, okay, given this universe of stuff, given these truth constraints that I want, please show me where. What is the minimum set of steps to reproduce the failure so I can correct or place an assert or whatever. This just assumes we didn't have the foresight to include the assertion, right? That's what bugs are, right? You just didn't see it. Of course, this is too simplistic. I mean, I'm not saying this is necessarily something that would actually occur, but I am saying it does give me an information that it's not obvious in other systems how you would get this, right? Whatever testing methodology you would have, most of your testing methodologies wouldn't be able to give you this information, right? Given the amount of effort that you put in. So what did I have to do? I had to generate some transactions. I had to make a very simple model. And now I have a lot more confidence than if I write. I'm confident. It doesn't matter who fixed it. Like you can imagine somebody says, oh, I'm going to take out this assert, or I'm going to go change the code, or I'm going to refactor it. You can still use this, right, in the face of changes to the code to prove that the code still does the right thing. And this is better than, again, than example-based tests, because when your tests fail, do they really actually tell you what went wrong? Not really, right? There's like, okay, this got violated, but it's not clear how did it get violated? And again, something else to point out is that this is not about testing in the small, right? So people often test like, is the model correct? Is the view correct? This is all about the hard stuff, which is that we know there is an actor in our system. They're going to create a series of related transitions to our state. Given that, is our program still correct? So this is not about, again, checking these little conditions. This is about checking actual streams of transactions that a user might produce. So for example, this is small, but let's start thinking about harder stuff where assertions would be annoying to write. For example, 7-step form. The user can set fields. They can go backwards. They can set fields. They can go forwards, set fields. There are lots of UIs that let you do this, but how are you going to test for that? Are you actually going to write tests to say the user went backwards, set a field, invalidated their email address, and then got to the last step, and does everything still make sense? You're probably going to not want to write anything that is a concrete test around that problem.
You'd only write that test if somebody reported the bug and you figured out how to fix it.
Yes. And even then, the problem with that is that you only possibly got one case of it. Yeah. You only got one case. Big caveat. None of this is to say that actually testing your models or actually testing your views or everything that you're doing, all valid. It's all valid. This is not an either-or system at all. This is just a new tool when you're like, we want confidence about very specific series of user interactions, and we can't write those tests. This is a way to write those tests you couldn't write before. Cool.
Even if you put your assertions into the application code, you'd still need something to generate a stream of actions.
That's right.
Run through the application.
Yep.
Or to handle the ones that are too computationally expensive to do, kind of like your back and forth.
Yeah. Oh, and just to drive this home, even though this example is very trivial, so two things I was talking to somebody that this system found, so using test check. Test check, two cases where it found bugs in problems that had nothing to do with what the person was looking for. So the first time this happened was Zach Tellman, who is a sort of big Clojure programmer. He was writing custom collections. And he was like, I want to write collections that look and act like Clojure collections. And I want to verify that all the properties hold. And then he was like, well, might as well test that Clojures hold. And so he ran, yeah. So he ran this thing for 24, basically overnight. And when he woke up, he was like, what? Something failed. And there was a bug in transients. And basically this code had been in production for 2-3 years. People had never seen it before. So it found a bug. He was trying to test his own stuff. It was like, I'm going to run on this other stuff, and then it found a bug. Another case, actually, with test check, somebody found a bug in Postgres, right? Somebody found a bug in Postgres. They're running their own tests against Postgres, right? They were just like, make this table, and I want to verify that my app is correct. And the sequence of operations that it generated uncovered a bug in Postgres, right? So I don't care how many assertions or how much testing you do, it's not possible for you to find these types of problems in very complicated systems, right? You can't write that type of testing code. You really need something to, A, generate some random series of events, and then actually give you a minimal set of steps to reproduce it.
Does the shrinking process that this uses have a good way of coping with non-determinism in terms of like?
Oh, yeah. So no. I mean, yes and no. Yeah. The great question. What about non-determinism? So if you have asynchrony in your system at all, so that's a huge problem. Once things go asynchronous, how do you actually make this work? And in fact, the model that I showed is a synchronous testing model. It is a synchronous testing model. But what's great about John Hughes is that they publish all their research, and you can download their papers. so they have papers on basically it's great where they basically you can basically supply a scheduler, to the testing mechanism. They explain in detail how you can do it. And literally, these types of papers are waiting for somebody to just fix this implementation, fix whatever language implementation to handle asynchronous testing. But that's a great question. Yes, this is great for synchronous testing, not so great for truly asynchronous testing. Other questions?
You briefly mentioned, where do you do the mocking in this code here?
So the mocking, so that's a good question. So I won't, so let's spend a little bit of time talking about that. So just to understand how Ohm works, and this is something I just didn't have time to get into because I don't want to, hold you captive forever. So what happens is when you make a request to the server returns a response, and the response matches your UI. We sort of said it implicitly earlier. That's actually awesome because that's actually what you want to test, and this test is not on the model because the model doesn't affect what the user sees, right? The actual data and their values doesn't matter. It only matters what is the presentation data. That's what you want to test. And so all my tests only test the presentation data. So here I say, I want to be able to read query expressions and also handle mutation query expressions. And I make a parser for it. So it takes a big expression and it runs the mutations and it does the reads. So here, what I need to do, the way that Ohm works, while this presentation UI data tree is really awesome for rendering, it's horrible for updates because of duplication. So I could have a person here in the UI and a person here in the UI. I don't want to have to update both places. So Relay, Falcor, and Ohm, they both normalize the data. So what we do is we take the response and we actually traverse it and dedupe it and move everything into tables, just like in a DB. So wherever people appear, we replace them with links. So that's why up here, I wasn't typing in things like ID name Laura. I just typed in this link to this other thing. So normalization removes all references and replaces them with links. Okay, so then what has to happen is that we replace all the dupes with links, and then this is the mocking thing. This is our application state. This would be what the UI would use. Down here I say, run the transaction that was randomly generated, and then here we say, give us the UI tree. So this is the opposite, these are corresponding operations. Go from a tree to something we can actually update easily. Go back to the UI tree. This is, in Ohm, this thing, you would pass it to render. You would actually call render on this. So this is the thing you want to test. And then down here, we actually get the UI entry for that, and then we check the data tree, the actual UI data tree. Is anybody in the tree self-friended? And we do a very similar thing for friend consistency. Looks exactly the same. So this is the mocking step. We build up the application state. We get the thing we're about to render, and we test that thing is correct. And this is really good because what does this mean? Remember, if you write stateless views, this is the benefit of writing stateless views. It's not possible for a stateless view to present anything that's not in the UI data tree already. They have to be the same, right? Like when you render.
So if I were to try to translate that, like say prop friend consistency, you're like creating a parser. You're creating something that like holds the global state. Then you're running the sequence of actions through the parser to change that state.
That's right.
And then that let line, is that like saying whatever the data that's going to be in my people component like is going to be fed by a query, so get that query and I want to run that through the parser in order to check the data that my people component is going to have?
Oh, okay, so good question. So what is this? So people, this is like in your UI, you always have to have a root view. You have a root view. So this is the root view, and the root view always has the total query. It always has to have the total query. So what this is saying, given this total query, normalize all the data into something that's more like a database. And then down here it says, given the total query, convert it back into something right before we're about to render it. That's all. This let binding, this is just like, in JavaScript, this would be var parser, var state, right? This is just local scoping. We're just putting them into local variables, and we're just using them. And This is saying, run all those mutations. And then down here we're saying, I mean, I could remove all the local variables. It's just harder to read, right? This is the local variables are just about reading.
Okay.
Is
That makes sense.
Other questions? No more questions? Okay, cool. Thanks.